This is the fourth lecture on my series on thermodynamics. In previous lectures, we have met the zeroth law, which essentially says that the property of thermal equilibrium is a transitive property. And what it says physically is that the quantity that we all know as temperature exists. In particular, it tells us that the equation which constrains the thermodynamic coordinates of two systems in thermal equilibrium must ultimately be equivalent to a form where one function of the coordinates of one system has to be equal to a similar but maybe altogether different function of the coordinates of the second system. So when two systems are in thermal equilibrium, some specific combination of their individual thermodynamic coordinates must be equal in the two cases, and that's exactly a quantity that we define as empirical temperature. And because of the existence of empirical temperature, we have this notion of isotherms, which really is short for isotherm curves. In the picture, we have shown a simplified situation where we are assuming that the thermodynamic state of each system can be specified with just two coordinates. That's simply so that drawing them on a two-dimensional graph becomes easy. And now you have isotherms which are labeled by fixed values of this function theta. So all the states here, xa ya, xa prime ya prime, xa double prime ya double prime, all correspond to the value theta 1 of this particular function. And so they will all be in thermal equilibrium with a state of the system B which lies on this particular isotherm curve. Similarly, all states of A which lie on this curve will be in thermal equilibrium with all states which lie on this one, and so on. Now in today's lecture, we are going to talk about the measurement of empirical temperature. And since empirical temperature is a mouthful, I will just say temperature from now on. Now the way in which temperature is measured is by using what is called a thermometer, as you all know. Now in thermodynamics, a thermometer is just the name given to a special kind of thermodynamic system, which I am calling tau for T for thermometer. But the speciality of such a system is that it should have an easily measured thermodynamic coordinate, which can be used to determine theta tau, the temperature of that system, by keeping all the other parameters fixed. Now this easily measurable quantity is called the thermometric parameter, and which systems can serve as a good thermometer and which systems can't simply depend on how easily measurable this one quantity, the thermometric parameter, is for that system, as well as how easy it is to maintain the values of the other parameters of the system at a constant value. Now, in order to do a measurement of the temperature of some system, what you need to do is to bring this thermometer in thermal equilibrium with the system whose temperature needs to be measured. The way you do that is to bring them in contact via diathermal wall. Of course, initially the two systems may not be in thermal equilibrium, but after a while the two systems will settle to an equilibrium situation. However, in this case, what you end up measuring using theta tau is the temperature that is attained after thermal equilibrium. So this process of bringing to thermal equilibrium disturbs the quantity that you are trying to measure. You are not really getting the initial temperature of the body. You are getting the temperature which it attains after it reaches thermal equilibrium with the thermometer. However, the basic idea here is that such disturbance can be made negligibly small by a proper design of the thermometer, and that also plays a very important part in choosing which systems can serve as good thermometers and which ones can't. Now, before we can use a thermometric parameter to determine this empirical temperature, we need to fix two things. We need to fix the size of the scale or the unit of temperature that we have to use, we also have to fix the origin of the temperature scale, the zero of the temperature, so to speak. We will illustrate the procedure for doing this using a typical thermometric system. Here we are going to use x as one of the coordinates which can be easily measured. This is going to be my thermometric coordinate. The other coordinates, well, I've just considered a situation where there is only one other coordinate y. That's because a two-dimensional system is easy to draw. However, you can think of all the other coordinates which are going to be held fixed during the process of temperature measurement as being sort of indicated by this one parameter y. So as you can see, what we are going to do is we are going to keep this y fixed at some value y0. Now, notice that we have drawn several isotherms of the system here. Out of all these isotherms, we are focusing on two in particular which are colored differently in the picture. The green one here is the locus of all states of my thermometer, the thermometric system, which would have been in thermal equilibrium had they been brought into contact with melting ice, or more precisely, a state where ice and water coexist. Similarly, the purple line here is a collection of all states of the system which are in or would have been in thermal equilibrium with boiling water. Again, more precisely, a state where water and steam coexist. Now, these two isotherms are special because they help us to establish the zero and the scale of temperature that we are using here. Note that y is held fixed at y0 as we said, and so when you bring the thermometric system in contact with melting ice, the value of x that you get is this particular value here, namely x0. Similarly, when you bring this in contact with boiling water, you get a value x100. x0 and x100 are basically numbers or quantities that you need to establish the zero and the size of the scale. In actual experiment, what you would do is you would bring your system, the thermometer, in contact with whatever state or whatever system you want to measure the temperature of, and then you're going to get a value xt for your thermometric parameter. Now, the way in which you translate this measurement xt into an empirical temperature theta is as follows. You essentially ensure that you get a value of 0 when you are talking about melting ice and a value of 100 when you're talking about boiling water. Of course, out of all possible temperature scales, I'm talking of a very special one, the so-called Celsius scale, which you're all familiar with. And if you want to change that result to the Kelvin scale, which we will hear a lot more about later, what we need to do is add 273.15 to that. We are going to take a very simple relationship between x and theta, a linear one, because that's the simplest. And of course, as we have already said, if anything can function as an empirical temperature, any function of that can also work as an empirical temperature. So let's start with the simplest one. The simple expression in this case would simply be theta equals xt minus x0 divided by x100 minus x0 times 100. Now this part would have given you the Celsius scale value, and if you want the Kelvin scale value, you have to add 273.15 to it. Now this essentially was the kind of scale that was used, at least until say 100 years ago, quite often, and is still in use now. Of course, this was not the only possible scale. We all know about the Fahrenheit scale, in which boiling water temperature turns out to be 212 units, or degrees Fahrenheit, and melting water temperature is 32 degrees Fahrenheit. In case any of you wondered why those numbers are the way they are, why 32, why 212, a big hint for that is your body temperature comes out to be suspiciously close to 100 degrees Fahrenheit. A bit less, of course, 98.4 to 98.6 or thereabouts if you are not experiencing a fever. But this acute closeness to 100 degrees should actually tell you that when Fahrenheit originally designed his scale, he actually wanted human normal body temperature to be 100 in his scale. And for 0, he had chosen something which would be very, very useful for people who live in colder climates. He essentially chose the temperature of ice-water mixture, so-called freezing solution. That is quite a lot colder than melting ice. And that's precisely why melting ice turned out to be 32 degrees Fahrenheit in that scale. And when later on people figured out that using the saltwater solution and the human body temperature is way too inaccurate for actual scientific things, they had to adjust back to more easily reproducible standards, melting ice and boiling water being the most commonly chosen ones. And that's where the Fahrenheit scale was redesigned to give you 32 and 212. Now, having said this scale has a problem that you have to actually accurately measure xt, of course, but you also have to measure x100 and x0 very accurately in order to get an accurate value for theta. In fact, any inaccuracies in x100 and x0 measurements will lead to systematic errors in all theta. All your theta readings are going to come out wrong. What's actually perhaps much more important in this case is that the temperature of melting ice is 0 degrees Celsius. This statement would be correct only if you had exactly 1 atmosphere pressure. Of course, the water and the ice used here would have to be very, very pure. And in fact, in more precise statements, you would also have to specify exactly what isotopic combination, in particular what heavy water to ordinary water percentage you would want in your sample. But the fact that any small change in pressure will actually change the melting point makes it very difficult to use this for high precision measurements. A very similar thing also creates a problem with boiling water, the so-called upper fixed point here. The temperature of boiling water depends on pressure even more strongly, and so controlling the pressure to a very precise value becomes very important in order to avoid error in this measurement. All this makes usage of these traditional scales or these traditional so-called standards of temperature much more complicated. Today we have a much better alternative. This better alternative is actually based on a very special state, a state in which water vapor, liquid water and solid water, all three can be in equilibrium with each other. This is the so-called triple point of water, and this happens at a precise point. Strictly speaking, a point in the PT diagram. There's only one value of P and only one value of T at which these three states will coexist. Unlike the boiling point, or more precisely, the vapor-liquid coexistence curve, which is a curve, a set of points where the temperature depends on the pressure, here we really have a true point. This happens at only one point, so if you have achieved the triple point of water, you know for sure that the temperature is exactly that of the triple point. There's only one temperature at which this is going to happen. So instead of using two different fixed points as in the previous idea, what we are going to do, or what we do nowadays, is that we actually use only one fixed point, at least for more high precision work. We essentially look at the isotherm of all states of the system which are in thermal equilibrium with or would be in thermal equilibrium with if brought into thermal contact with water at its triple point. measure that particular value of the thermometric parameter, the so-called XTR, and of course measure XT, the isotherm, which contains all states that are in thermal equilibrium with the state whose temperature you are trying to measure. And then use a much simpler resulting formula here. X by XTR is the empirical temperature. This of course only fixes the size of the scale, but the zero of this is already predetermined as something called absolute zero. We will have a lot more to say about absolute zero later on when we talk about the absolute temperature scale. For the time being, I'm sure most of you know what the absolute zero of temperature is, at least in terms of the ideal gas law. But there's a much more physical reason for this thing being important in thermodynamics. But we are going to come to that later once we have covered the second law. Indeed, X by XTR would have been a perfectly good measure for theta. But because we want our results to agree, at least in the vicinity of the triple point, to the standard definition of temperature that has already been established before, we are going to multiply this quantity by 273.16 Kelvin. This is because the triple point of water occurs at 0.01 degrees Celsius or exactly 273.16 Kelvin. By the way, the fact that triple point of water occurs at 273.16 Kelvin is an exact statement because that's exactly how you fix your temperature scale. So, whatever you do to fix your temperature scale, the triple point will always come at 273.16. Other temperatures that you measure using the scale could very well depend on which precise physical quantity you are using as your thermometric parameter. Using different physical quantities will actually give you different values of theta for the same system. That is, if you take a single system at some temperature away from that of the triple point and bring that in contact with various different kind of thermometers, the theta you get from them would actually turn out to be different. The only one for which you are guaranteed to get the same value of theta is where by definition you are going to get 273.16 Kelvin, namely at the triple point. So when you use different temperature scales, you would also have to figure out a way of connecting one temperature scale to another. So there should be some monotonic function which connects one scale, measurements using one thermometric parameter, to that carried out using another thermometer, some different thermometric parameter. The exact connections between different scales does not really concern us very much here, but it is important to know that such connections can be made. Let us now take a brief look at some of the more popular kind of thermometric systems that are used, what kind of controlling parameters are held constant there, and what thermometric parameter is actually measured. Our first example of a thermometer is one that is bound to be familiar to most of you. I would have said all of you, except that in very recent days its usage has been reduced a bit. So some of the more younger viewers may not have seen this. But almost all Indian kids have had this stuck in some part of their anatomy at some time or the other to measure their fever. This is what is typically called a medical thermometer. And here, the system is really a mercury column which is stored in a glass capillary, and the thermometric property that is measured in this case is the length of that column. The next thermometer that I'm going to talk about is more seen in labs rather than in daily life. This is basically a thermocouple which is maintained under constant pressure and tension. The pressure and the tension here are what was clubbed as the parameter Y in our discussion a while ago. And here, the thermometric parameter that is actually measured is the thermal EMF generated because of a temperature difference between two junctions of the thermocouple. The third one is again a very standard measuring instrument which is used in labs. This is the platinum wire which has been maintained under constant pressure and tension. Again, these are the parameters that we clubbed as Y before. And the thermometric parameter that is measured, the X in this case is R, the resistance of the wire. Now, as I've said, if you directly take these thermometric quantities, divide them by their value at the triple point, and scale them up by 273.16 Kelvin, they will agree only at the triple point exactly, and in the vicinity of the triple point, their values will come close to each other. Of course, when you go very far away, you typically have to figure out how one temperature measured by one of these substances is related to the temperature measured by any other substance. The same actually holds for our final two examples. The first one is gas maintained at a constant pressure. Here the volume of the gas is the thermometric quantity, and essentially you can define the temperature to be volume divided by volume at the triple point multiplied by the scaling factor 273.16 Kelvin. But perhaps a more practical one is gas at a constant volume. Here the thermometric quantity is the pressure of the gas, and the reason why this is more practical than the previous example is rather simple. It's much easier to precisely measure the pressure and maintain the volume at a constant value for a gas than it is to measure a volume experimentally. And as a result, you get a more precise measurement using the constant volume gas thermometer, which was our final example. Now let me just take a look at this at a bit of detail. This is a schematic diagram of the constant volume gas thermometer. A real practical one in the laboratory would have some additional embellishments, but the basic idea can be conveyed by this. Here, the gas bulb contains the gas which is our thermometric substance, and it is this gas bulb which has to be brought into thermal contact with the system whose temperature is to be measured. The gas bulb is connected to the mercury column through a thin capillary, so this is where the gas ultimately expands into, and you have mercury in this U-shaped structure here. There is a level which is indicated on this side, this arm labeled M prime, and what you can always do is that you can keep the volume of the gas inside fixed. This is the constant in the constant volume gas thermometer, by ensuring that the mercury column here always comes up to an indicator level. And you can do that by adjusting the height of the mercury in the other column by raising or lowering it. In this case, the difference in height of the two columns gives you exactly what the pressure of the gas is, or rather, this actually gives you the pressure excess over the atmospheric pressure. There are other technical advances that you can make to this system so that you can automatically compensate for fluctuations in the atmospheric pressure. I'm not really going to go into those details right now. But this P, and of course, divided by P at the triple point, times 273.16 Kelvin will be the temperature as measured by the constant volume gas thermometer. Now, as I have kept on saying over and over again, the measurements that you make using these different thermometers would match only at the triple point and will match somewhat approximately in the vicinity of the triple point. But when you are far away from the triple point, you will need ways of connecting the temperature measured by one to the temperature measured by another. We very often don't even say temperature measured by the platinum resistance thermometer. We often use a formula or a table to convert the resistance measurements directly to measurement done using some other scale, like this constant volume gas thermometer scale. But that's just a matter of detail. Now, all of these are very specific to the kind of system you use. They have their advantages and their disadvantages. And the main reason why you have to use so many is that, for example, a gas will stay gas only over a region. and may not stay a gas if the temperature is lower too much. The platinum may melt if you are trying to measure too high a temperature. A thermocouple may malfunction at high temperatures, etc., etc. So there is nothing really very universal about the temperature that you measure using these scales. And frankly, there is no reason to consider one scale as superior to the other. All of them are roughly on the same footing. However, among all these empirical temperature scales, there does happen to be one which is actually special in a very well-defined sense. This is the so-called ideal gas scale, and that is what we are going to describe at the last part of today's lecture. Now, when you call something an ideal gas scale, an objection comes immediately to mind. As you all know, ideal gases do not really exist. They are idealizations of real gases. So all the thermometers that I have described so far actually can and are realized in a lab, at least, if not in daily life. The very first one that we talked about actually is also used very often in daily life. But this ideal gas scale seems like something which is sort of a theorist's pipe dream and not really a real measuring instrument. But frankly, it is really not made using an ideal gas. It's actually made using a very real gas. Or rather a series of very real gases. And the system that we use to create this special thermometer, the ideal gas scale thermometer, is basically what we just described. It's a gas confined to a constant volume. If you want to do high precision measurements, you will have to have special additional design features which will compensate for the atmospheric pressure, let's say, and other effects. But that really is all there is to it. And the thermometric parameter here, of course, is just the pressure and the formula by which you calculate the temperature of this gas. Note that I am writing T here as opposed to theta because I want to give somewhat special status to the scale. Is defined to be P divided by P at the triple point into 270.16 Kelvin. But this, of course, is nothing new. This is just the constant volume gas thermometer scale. And the pressure that you measure when you bring the system in thermal equilibrium with some specific system depends on the volume and the amount of the gas. Now that, of course, is cured already by dividing by PTP. So the P by PTP ratio is actually independent of the amount of the gas and the volume of the gas. Almost. Now, as before, in fact as always, in the modern way of looking at things, the triple point of water is used as a standard temperature, and hence I find the value of 270.16 Kelvin, which, as we have stated already, is done to maintain historical tradition. If we did not have the weight of historical tradition, we might have just dropped that factor or maybe replace it by something more convenient like say 100 or something. But we really can't do that. There are too many measurements that we have done already which uses this standard scale. Now, what is very important is the following. If we were to create such constant volume gas thermometers using different gases, typically simple gases are not very reactive or complex molecules, say helium, hydrogen, nitrogen and so on. The important thing is, if you look at the value of the theta that you get using this P, this theta is actually, despite what I said a while ago, not really the ideal gas temperature. It is just P by PTP into 270.16 Kelvin. And here what we have done is we have plotted graphs of what you get for this theta when a constant volume gas thermometer is brought in thermal equilibrium with a very specific state. Steam, or rather a situation where water vapor and water is coexisting. The so-called boiling point of water. As you can see, if you use different gases nitrogen, hydrogen, helium, you actually end up with different values for the measured value of theta P. However, as you decrease the pressure at triple point, which you can do by reducing the amount of gas inside your constant volume thermometer, then something strange happens. All of these measurements change a bit. So P by PTP, taking that ratio, does not completely cure you of this gas dependence, but does reduce it a bit. But what is very, very important is that as you make the PTP smaller and smaller, all of these different measurements go to the same limiting value. This happens not only at the boiling point of water, it also happens, say, at the melting point or at any other standard temperature that you would care to use. So now you have a kind of universal scale. This scale actually depends on the gas, except of course at the triple, where it has to give you 273.16 Kelvin. But as you reduce this amount of the gas so that PTP falls to 0, then the scale becomes the same for all gases, irrespective of which gas you are using, or at least most gases to be more precise. This universal scale, universal in the sense that it is the same for many, many different gases, is called the ideal gas scale. So T ideal is pressure by pressure at triple point multiplied by the scaling factor to 73.16 Kelvin. But when you take the limit of this ratio as PTP goes to 0. Now this ideal gas scale happens to be very, very important in thermodynamics. At this point, the ideal gas scale is still an empirical one. It is perhaps better than a hydrogen-based one or a nitrogen-based one or maybe a helium-based one, but not really much better. And at this stage, there is no real reason why we should consider it as something very special. However, we will see later that this scale happens to coincide with a temperature scale, which has inherent thermodynamic significance over and above the significance which all temperature scales have. That is, they all talk about thermal equilibrium or lack of it. This particular scale happens to coincide with what we call the absolute scale or the thermodynamic scale of temperature. But that is something we can only establish later on in the course after we talk about the second law of thermodynamics. But before we can come to the second law, we have to of course go through the first. We are going to lay the groundwork necessary for the first law in our next lecture.